We have 3 talks left this afternoon. All talks are pre-recorded, so I'll be playing the recording for the second talk of the afternoon track just in a second. Just to remind you during the presentation to keep your microphones muted, and please make sure you don't accidentally share your screen so that everybody sees the video for the presentation. After the talk, there will be a 10-minute Q&A session. You don't need to speak your questions. Please type them in the chat window in the Teams interface. We even invite you to write down your questions during the talk, so that way we can see the questions coming before the end of the talk, and Rebecca will read the questions aloud to the presenters. Yeah, I think we're ready to go. So with that, I will switch over to the video presentation and present the speakers. Please bear with me. Okay, so the next talk is called Generative Latent Neural Models for Automatic Word Alignment by Anh Khoa Ngo Ho and François Yvon. Here we go.
You might need to also share the computer audio.
Yes, we're missing sound.
Excuse me?
We're missing the audio. I think you said if you share computer audio.
Thank you. Yes, I have to go back there. Sorry for this. It is complex to do these things every time, get them right every time. So I'll restart it and unshare, reshare. I'm sorry for this. So.
Discussing the paper Generative Latent Neural Models for Automatic Word Alignment. First, let's begin with word alignment. Word alignment is one of the basic tasks in natural language processing. It aims to identify translational equivalences at the level of words in parallel sentences. We could see an example of word alignment between one sentence in English and another one in French. We have links between it and ceci, is and and so on. We propose and assess several evaluations of a vanilla rational autoencoders for the task. We demonstrate that these techniques can yield competitive results as compared to GISA++ and fast align and to a strong neural network alignment system for 2 language pairs, English-French and English-Romanian. Compared to the popular GISA++ IBM1 model, our approach improves alignment accuracy by 14 on English-French and by 5 on English-Romanian. Take a look at the line of research. From the traditional alignment models, namely IBM models, HMM model, to neuron-based approaches, Agnoli, Wang, just to name a few. And then there is the model of Rios, which is our main source of inspiration. They consider rational autoencoders of Kingma and Welling. In our approach, we revisit here this model and we try to extend it. Now I will cover neuron word alignment rational models. I first show how to model word alignment and describe the fully generative model based on the approach of Rios. In my works, I generalize this approach. initially devised for IBM Model 1 to the HMM model. I also explore ways to effectively enforce symmetry constraints with parameter sharing and enforcing agreement in alignment. I finally study how these models could benefit from monolingual data. The standard approach to probabilistic alignment is to consider asymmetric models, associating each word in a sub-sentence of J words with exactly one word from the target sentence of I plus 1 words. Target sentences are completed with a null symbol, conventionally at index 0. This association is governed by the unobserved alignment variables A. As can be seen in the equation 1. The two terms in the inner product are referred respectively as the distortion model and the translation model. I now describe the generative story. Model generates a sequence of latent variables, which means a sequence of d-dimensional random embeddings by sampling independently from some prior distribution. For example, in this approach, it is Gaussian distribution. Model then generates target words E conditioned on this latent variable sequence Y. Model then generates the alignment variables A, denoting the alignment from the source sentence F to the latent variable sequence Y. This could be based on the uniform distribution of Markovian dependencies. Finally, model generates subwords F conditioned on the latent variable sequence and the alignment variables A. The decomposition of the joint distribution of the source and target sentence is shown in the equation 2. We consider tractable alignment models and use the variational distribution only for modeling the latent variable sequence Y conditioned on the target sentence. This yields the objective function in the equation 3. This objective is a sum of three terms that are referred respectively as the reconstruction cost, the alignment cost, and the KL diversion cost. To clarify the approach, let's take a look at the graph. This is an encoder, encoding the sentence E and generating the latent variable sequence Y. Each target word E has a latent variable Y. There are two decoders, one for generating the sentence F and another one for reconstructing the sentence E. Note that Y0 is from the special token null used for underlying words, and the model does not reconstruct this token. Our first variation of this model considers a richer transition model, assuming Markovian dependencies. First-order dependencies are taken into account. Alignment positions only depend on the jump width and not on the absolute index positions. Note that the exact marginalization of alignment variables remains tractable with the forward algorithm. The alignment cost can be seen in the equation 4. Take a look at the two directional models from sentence F to E and from E to F. We see that there are two decoders generating target side E side and two decoders generating source side F side. Therefore, parameters sharing between the decoders of both alignment directions helps to encourage these directional models to share information and to improve their joint performance. This is our second variant. This is one important benefit of having a fully generative model in both alignment directions. The joint objective function now includes 6 terms, 2 reconstruction costs, 2 alignment costs, and 2 KL diversion costs. From this, a first benefit is that it greatly reduces the number of parameters to train. We also expect that it will yield 2 additional benefits. It helps to improve the alignment model, which is more difficult to train for lack of observing the right alignment variables. For example, look at the direction F to E. The reconstruction of sentence E from Y helps to improve the decoder E. Another benefit is that it makes the alignments more symmetrical, thereby facilitating their interpretation and their recombination. Our third variant, we add an extra cost that rewards agreement between asymmetrical alignments. We expect that controlling the level of agreement between alignments helps to improve these asymmetrical alignments. The costs are based on the alignment posterior distributions that can be computed effectively using the forward-backward algorithm. For non-known alignment links, the model tries to reduce differences between two asymmetrical alignments, as can be seen in the equation 7. For known links, the agreement term should reward configuration where one subword is aligned with the known symbol aj equal 0 in one direction. It is not aligned to any target word in the other direction, as can be seen in the equation 8. Another benefit of this approach is that the autoencoder can be trained monolingually. We use supplementary monolingual sentences in the encoding-decoding process, which means adding an extra monolingual reconstruction term as in the equation 9. We also consider training the alignment model monolingually. We implement this idea by adding a random noise to the target sentence to make it more similar to a source sentence and amenable to alignment. The new extra monolingual reconstruction term is shown in the equation 10. Note that IBM Model 1 used our alignment model. The noise model follows the technique used in Lambo 2017. There are two steps. It randomly deletes input words, then slightly shuffles the sentence, where the difference between the position before and after shuffling each word is smaller than 4. For example, the word is and the punctuation are deleted, then the sentence is shuffled. I finally have the sentence. It's understandable, quite. Now I show the experiment. I discuss the datasets, how the implementation are, how to evaluate the models, and finally, the results. Our experiment used two standard benchmarks from the 2003 Word Alignment Challenge for English, French, and English Romanian. For French, we use a large training corpus of parallel sentences, whereas in the case of Romanian, the training data is limited in size. It can be seen in the table. We perform the alignment between subword units generated by byte pair encoding with 32,000 vocabularies. Now we need to convert subword level alignment into word level alignment. To do that, a link between the source and the target word exists if there is at least one link alignment between their subwords. For example, we have a link able, so the English word understandable aligns with the French word compréhensible. All models are close in structure to the model proposed by Yost and are made of three main components, one encoder and two decoders. The encoder is composed of a token embedding layer, two LSTM layers, each comprising 64 units, and the dense output layers to independently generate the mean vectors and the diagonal of the covariance matrices. The vector y0 is independently generated from a pseudo sentence made of one dummy token. It is identical for all target sentences. Note that the decoder model does not try to reconstruct this token. Now, our two decoders, reconstruction decoder and alignment model with emission and transition components. Note that for the alignment model, only emission component parameters are shared in sharing parameter approach. Note also that jump values for transition component is in the interval from minus 150 to plus 150. Evaluation protocol. We use the alignment error rate, accuracy, F-score, precision, and recall as measures of performance. AER is based on a comparison of predicted alignment links with a human reference including show and possible links. Note that English-Romanian reference data only contains show links. In this case, AER and F-score are related. Results with symmetric alignments use the Rhodia final heuristic. I report the AER score of the baselines, including the Gauss-based model, is a plus fast aligned, and the two neuron variants operating at the word and subword levels. I'll compare these models with all three variational autoencoder variants. Our first observation is that neuron baselines are better than Giza++, and that use PPE units brings an additional gain. The vanilla rational models IBM1 falls short to match these results, and proves way worse than the two neuron versions of the IBM Model 1. These two results are in line with the finding of Rios, who report similar difference in performance. We see that sharing the parameters between directions greatly improve this baseline with a reduction in AR of about 8 points for English French and 6 points for English Romanian for both directions and ways for symmetrization. We also observe that the gain is more significant when the morphologically rich language French Romanian is on the target side. This is where the emission model is weakest and benefits most from parameter sharing. Adding an extra agreement cost falls to produce better alignments for English-French. We, however, observed again about 2 points for the symmetrical alignments in English-Romanian. For HMM models, both symmetrization strategies prove very effective to improve the basic rational autoencoder models, and our best system, AC, achieves scores that are close to the HMM neuron baselines at PPE level. One possible issue is that we do not fully solve via symmetrization, and is related to the null token, which I explained above is not part of the reconstruction model and which do not improve with joint learning. I'll show a small story about balancing the cost terms in the objective function. I discussed that one possible issue is related to the null token. Therefore, I'll analyze the problem of unaligned words. And I finally analyze how our evolutions improve alignment performance in detail. One well-known issue of rational autoencoder for text applications is posterior collapse, where the rational distribution collapses towards the prior distribution. This is because the KL term can get arbitrarily small, with a moderate effect on the reconstruction cost, assuming a strong reconstruction model. We also encountered this problem in our setting, but the interpretation is a bit different. When the KL term goes to 0, all words in the dictionary become distinguishable and the reconstruction cost reaches its maximum, corresponding to the entropy of the uniform distribution of the target's vocabulary. Therefore, we apply a similar approach using larger weights for the reconstruction term and even more for the alignment term. Let's take a look at non-alignment links, the alignment accuracy for English-French. We observe that the number of underlined words varies in great proportion, with a minimum of about 3,000 words in neuron baseline at word level HMM plus NN, and a maximum of nearly 6,600 in vanilla rational models HMM, VAE plus PPE. We see the inability of all models to correctly predict null links, the best model achieving a precision of only 13.1%. We also see here the effect of the symmetrization constraints, where the tendency of non-element links is reduced, yielding better accuracy than the vanilla rational autoencoder. To sum up, the rational autoencoder-based approach tends to leave too many words underlined. This is because of lack of having a proper model for the latent representation of the null token. Improvements by sharing parameters. We see the clear benefits of sharing parameters, which contributes a jump of both precision and recall compared with the rational autoencoder baseline. This enhancement helps to outperform Giza++, but is insufficient to surpass the conventional neural network models, especially when using PPE. We also see that the gain in recall is largest in the direction English-Romanian from about 35 to about 43. This is because the better reconstruction of English words improves the translation model. We note that the model iterating agreement cost leads to a higher number of agreements in comparison to the other rational autoencoder-based models, about 800 links. It also yields better scores in terms of intersection AR, about 8 points. The last extension concerns the use of monolingual data in the low resource condition. We see that the model helps to improve the reconstruction model, which attains a most perfect reconstruction accuracy in both directions, suggesting that the autoencoder is overfitting. The gain brought by monolingual data is found only for IBM 1. For the direction Romanian English, about 3.6 points. The extra task of denoising the input, the model noise, further improves the AERs compared to the parameter sharing approach, about 2 points. In this paper, we have revisited the proposal of Rios and explored variants of rational autoencoded models for the unsupervised estimation of neuron word alignment models. Our study has confirmed the previous findings and highlighted two promising aspects of this model. First, is a full model of the joint distribution, which makes it easy and natural to introduce symmetrization constraints, as we have shown by proposing two such extensions. Second, it appends new alleles to also incorporate monolingual data during training, which might especially prove useful in low-resource scenarios. One remaining problem in this approach is the prediction of the null links, which is quite problematic in an encoder-decoder approach. We have shown in particular that the rational autoencoder model is strongly inclined to under-generate alignment links, which is detrimental to the overall AER performance. Symmetrization is the first answer to this problem, which however only partly fixes the issue. Another difficult problem with this model is controlling the optimization problem, a difficult task when the objective functions combine multi-terms with varying dynamics. More work is needed there to design better optimization strategies with a better balance between the various sub-objectives.
All right, thanks for that talk. We have one question that I think has already been answered in the chat, and I'm going to ask a quick follow-up to that, and then I see one more coming after that. So Kevin's first question there was whether the alignment variables were one-to-one, many-to-one, or one-to-many alignment. And the reply there was that they generate one-to-many alignment and one-to-one alignments, but the BPE allows for the generation of many-to-many links. So I just want to check that I've understood that. So it's a bit of a follow-up to Kevin's question. Is it when you say that BPE helps to generate many-to-many links, that's talking about how you created those new links based on any single link that existed between BPE subwords. Is that right?
Yeah, that's right.
Great. Thank you. All right. Kevin's next question there. Any thoughts on how these kinds of latent alignment models might also help neural machine translation systems, not just the alignment task, but generation itself?
Well, normally we see there are a lot of research that's using the result of word alignment into attention-based model. So it's good help for improving the score, the performance of neural machine translation systems. And basically using this approach, we can see that we could have a share latent variables. It's like the representation of both the source and the target sentence. So in this case, we could use this for some tasks, for example, data augmentation.
Thanks. The next question that I see in the chat is, which reference sets did you use to compute the AER scores, and are they publicly available?
The both score is published, available, I think. The reference is from, let me check. It's from a research, it's from the 2003 Word Alignment Challenge. And I think you can find easily on the internet, I think. You can see also the link in our paper. Yeah.
Thanks. Are there any other questions? Oh, there is another question. Are there any tests on human interaligner agreement? All right, actually, I have a clarifying question on that question. Are you, is that in reference to the test sets that are being used, or to human evaluation of the output?
Well, you mean that we have already the interaligner agreement? Any reference for us, or?
I'm not sure. Maybe if Michael, if you could clarify this question. Oh, okay. Do the reference sets you used have multiple alignments, and where was human agreement measured on those multiple alignments?
No, actually, our result was just based on we are only based on the already tests that we could find on the internet. So there are no the cross check, I think.
So if I may, I guess that Michael is referring to the fact that a lot of these reference alignments, there have been some questions raised at some point about whether they were actually reliable, and I think that there were issues with inter-annotator agreements, and one of the facts being that word alignment is not a very well-defined task, and two humans will typically come up with different solutions to the same question, and so this raises the question whether very small differences in performance for your aligners are significant. If they fall within the range of standard disagreement between two human aligners, and maybe this is something that that you would want to look into.
And I think since we only have 1 minute left, Michelle, I'll let you wrap up this session.
Okay, well, thank you very much, Anh Khoa. So this was the second talk, and as I mentioned, we have to move over to another meeting room for the third talk of the afternoon. So I'll see you all in room R7 research track something. Okay, thanks again to the speakers.